I think the popular myth of programming, well, at least the one you see in movies anyway, is that it's this completely frictionless, almost magical transaction.
Right, like the hacker typing frantically in a dark room.
Exactly. You write the logic, the processor executes it at the speed of light, and everything just miraculously works. But, I mean, anyone who has actually shipped a single line of code into a production environment knows that the reality is entirely different. The reality is essentially just chaos management.
It absolutely is. I mean, we spend an enormous amount of time obsessing over the syntax of building things, right? But the invisible architecture of software engineering is actually about what happens when those things inevitably fall apart, because they will.
They always do.
Welcome to the deep dive. Today, we are looking at the anatomy of a computer crash. We are taking the core insights from Harvard's CS50 on Python exceptions, but our mission today isn't to just read a technical manual to you.
No, nobody wants that. Definitely not. We want to figure out how developers actively anticipate chaos and, like, build safety nets right into their logic.
Okay, let's unpack this because to build a resilient system, you first have to understand the specific vocabulary Python uses when things break.
Yeah, and that vocabulary is incredibly precise. Before you can intercept a failure, you really have to understand the exact flavor of that failure. The material highlights three distinct types of errors that form the baseline of this language.
Right.
So we all know the frustration of a syntax error. The interpreter hits a mangled piece of code, maybe a missing colon or an unclosed bracket, and it just halts.
It just gives up.
Exactly. It literally cannot parse the instructions. It's a fundamental failure in the grammar.
Right, but what is way more interesting to me are the failures that happen when the grammar is completely fine, but the context is wrong, like a value error.
Oh, those are the best. Or the worst, depending on your perspective. True. I mean, my absolute favorite way to visualize a value error is to imagine a perfectly functional microwave. Its whole job is to heat things up. Now, imagine you try to put a muddy hiking shoe into that microwave.
Okay, a shoe.
Yeah. Technically, you're giving the machine a physical object. The door closes, you hit start. But it is fundamentally the wrong type of object for that context.
Right.
The machine knows how to heat food, but it's going to have a catastrophic problem trying to process footwear.
That is a perfect encapsulation of a state mismatch. In a program, you might have a function designed to calculate age, right? And the user inputs the string 22, but they spell it out with letters instead of typing the integer.
Right, like TWENTY.
Exactly. The processor completely understands the operation, but the value itself is unworkable. And that brings us to a slightly different existential crisis for the computer, which is the name error.
The identity crisis.
Yeah. This occurs when the code references a variable or a function that simply does not exist in the current namespace dictionary.
So it's basically asking for a relationship with an entity that was never born.
Precisely.
But let me challenge the design here for a second. We talk endlessly about how advanced modern interpreters are. If Python is so incredibly smart, why the dramatic crash?
What do you mean?
Like, if I misspell a variable name slightly, or pass a string instead of an integer, why does the interpreter just throw a name error or a value error and just completely give up? Why can't the compiler just look at the surrounding context, infer what I obviously meant, autocorrect it, and keep the system running?
What's fascinating here is that this strictness is not a limitation of the interpreter. It is a fundamental, deliberate design philosophy.
Deliberate.
Absolutely. In software architecture, ambiguity is the ultimate enemy. Think about the implications of an interpreter guessing your intentions.
Okay.
It might guess right 9 times out of 10, but on the 10th time, it might guess that instead of writing to a local cache, you meant to drop an entire production database table.
Oh, wow. So an incorrect guess at a massive scale. That would be a resume-generating event.
Exactly. These errors are strictly designed diagnostic tools, not punishments. By throwing a hard error and crashing, Python is forcing the human to be explicit.
I want you to take the wheel.
Yeah, it's effectively saying, I am not going to guess, because guessing leads to catastrophic silent failures. It forces the developer to take absolute responsibility for the logic.
So it is always better to fail loudly than to proceed incorrectly in silence.
100%.
But, I mean, if we accept that loud failure is the intended design, we hit a practical wall, right?
Okay.
In the real world, you cannot control user input. Users will constantly hand your microwave a shoe.
They love handing you shoes.
Right. You cannot have an enterprise software system or a web server crash entirely every single time someone makes a typo. So how do we isolate that loud failure so it doesn't just take down the entire application?
And that shifts us from just observing failures to actively managing them. This brings in Python's defensive mechanisms, which are the try and accept blocks.
Okay, here's where it gets really interesting. Because this is where the developer stops being a victim to unpredictability and starts playing defense. Let's look at the mechanics of how this actually operates in memory.
Sure, so under the hood, the try block acts as a highly monitored sandbox. You take the potentially dangerous code, so like the network request, the file read, the user input, and you execute it inside this block.
Okay.
You are telling the Python interpreter, attempt to execute these instructions, but monitor the call stack closely for any exception objects being generated.
And the accept block is the catcher's mitt waiting right below it.
Exactly. If the code inside the try block executes perfectly, the accept block is entirely ignored by the compiler. It's like it's not even there.
But if things go south?
If a failure occurs, say a value error is generated, the program does not instantly crash. Instead, the interpreter unwinds the call stack, looks for an accept block designed to handle a value error, and if it finds one, it intercepts the exception object midair. The execution flow is immediately redirected into the accept block, allowing you to run recovery code. You can log the error, print a polite message to the user asking them to try again, and the main application just continues running seamlessly.
I always visualize this like a movie stunt double.
Oh, I like that.
Yeah, like the main actor is the try block. Most of the time, the actor's just delivering lines, walking through doors, totally safe, standard execution.
Right.
But then there is a dangerous sequence. You try the stunt, but if the danger level spikes or something goes mechanically wrong, the accept stunt double instantly steps in to take the fall.
Yes, that's exactly it.
The director doesn't have to shut down the entire multi-million-dollar production. The stunt double absorbs the impact, the dust settles, and the movie just keeps filming.
That analogy maps perfectly to the execution flow. The production continues. However, an inexperienced director can actually misuse that stunt double in a way that just completely ruins the film.
Which is exactly where I wanted to push back. Wait, if the accept block is so good at intercepting crashes, isn't there a massive temptation to just wrap your entire application in a giant try accept block and just catch absolutely everything?
Oh, people definitely do that.
Just ignore the specific errors and force the server to stay alive no matter what happens.
Yeah, and you have just described one of the most dangerous anti-patterns in software engineering.
Really?
Yes, it is known as swallowing exceptions. If your accept block is too broad, like if you just tell it to catch any error without specifying whether it's a value error or a type error, you are essentially putting a piece of black tape over your car's check engine light.
Okay, so the annoying light is gone, but the engine block is still going to melt.
Exactly. Let's say you have a generic catch-all accept block intended to politely handle bad user input. But one day, your database server goes offline. Your code tries to connect, fails, and throws a critical connection error. Your overly broad accept block catches that critical infrastructure failure, assumes it was just a user typo, prints please try again, and keeps running.
Meanwhile, user data is actively being dropped into the void because the database is gone.
Yes. And you, the developer, have absolutely no idea because you swallowed the alarm.
Wow. So targeted defense is the only viable strategy. You only wear a catcher's mitt for the baseballs you expect to be thrown.
Exactly.
If a grand piano falls from the sky, like a database outage or a fundamental syntax error, you do not try to catch it with a mitt. You step back and let the program crash loudly because a crash is the safest response to a piano falling.
That is the essence of resilient design. You only catch what you specifically know how to recover from. But, exception handling isn't just about managing the disaster.
What else is...
Well, if we are keeping these try blocks as tightly scoped as possible, only wrapping the truly dangerous lines of code, it creates a logical puzzle. What do we do with the code that heavily depends on the risky operation actually succeeding?
Right, because if I successfully download a file in a try block, I need to actually process that file. But if I don't want to shove all my processing logic into the risky try block, which, that makes debugging a nightmare, where does it go?
This is where Python introduces refined control flow with the else block.
The else block.
Yes. In the context of exception handling, else is specifically designed for dependent success. The code inside the else block will execute if and only if the try block completes its execution without generating any exceptions.
Okay, let me try a mechanical analogy for this one.
Go for it.
Using try, except, and else is like wiring a new electrical outlet in your house.
Yeah.
The try block is the physical act of connecting the wires. It's dangerous.
Very dangerous.
The accept block is your circuit breaker. If you wire it wrong and cause a short, the breaker trips, intercepting the failure before your walls catch fire.
A targeted interception.
Exactly. Now, the else block is plugging in your brand new expensive television. You absolutely do not plug the TV in during the dangerous wiring process. You keep the tri-block isolated.
Right.
But you also only get to plug the TV in if the wiring was successful and the house hasn't burned down. The else block separates the risky action from the dependent reward.
That is spot on. It isolates the risk while maintaining the logical dependency, but the control flow nuances don't stop at success.
There's more.
Yeah.
Yeah.
If we connect this to the bigger picture of system architecture, there are times when the correct, deliberate response to a caught error is total inaction.
Wait, but the Python compiler hates empty blocks of code. If I write an except block to catch a specific warning, but I don't put any instructions inside it, the compiler throws an indentation error. How do you communicate deliberate inaction?
You use the pass keyword. Pass is fascinating because it is explicit silence.
Explicit silence.
Yes, it tells the Python interpreter, I acknowledge that this specific exception occurred, I successfully intercepted it, and my architectural decision is to do absolutely nothing. Move on to the next line of code.
I do this in my daily life constantly.
Oh,
Yeah, using pass is the exact equivalent of dealing with a spam caller.
Oh, that's good.
You look at your phone, you see the incoming call.
Yeah.
That is the exception triggering. You recognize the number. Now, you could hit the red decline button, sending it straight to voicemail. That is an active error response.
Right.
But instead, you just stare at the screen, let it ring out silently, and go back to drinking your coffee. You explicitly chose to execute no action.
And from an engineering perspective, pass acts as a crucial signal to the next developer who reads your code.
How so?
When a senior engineer sees a pass statement inside an except block, they know the original author didn't just forget to write error handling or swallow an exception by accident. They know that silence was a deliberate, calculated design choice.
Deliberate design. I really like that framing. But everything we have discussed so far has fundamentally been reactive, hasn't it?
What do you mean?
Well, Python dictates that a mechanical failure happened, like a value error, a name error, and we react to it. We catch it, we bypass it, or we execute dependent logic. Yeah. But what happens when the mechanics of the code are perfectly fine, but the business logic of our specific application is completely broken?
Ah, that is the threshold between a junior programmer and a software architect.
Okay.
To truly master a system, you have to transition from reactive defense to proactive offense. You have to be able to dictate your own parameters for failure.
Dictate your own failure.
And you do that using the raise keyword.
So instead of catching a crash, I am intentionally initiating one.
Yes, you are forcing the generation of an exception object. You use raise when a situation violates the laws of your specific universe, even if the Python interpreter thinks the operation is perfectly mathematically sound.
Give me an example of that.
This raises an important question. Well, let's look at a classic banking software example. Imagine a user attempts to withdraw -$50 from their account.
Right. Mechanically, Python sees an integer variable, and it sees a subtraction operator. It doesn't know what money is or how banking regulations work.
Exactly.
Python is perfectly happy to subtract -50 from an account balance, which mathematically would just add $50 to the account.
Exactly. The interpreter will execute that operation flawlessly, but from a business perspective, that is a massive exploitable failure. The mechanics are fine, but the logic is disastrous.
So what does the programmer do?
The programmer uses the raise keyword to manually trigger a value error. You are effectively telling the system, I do not care that the math compiles. This input violates the rules of my application. Halt the execution flow immediately.
You are pulling the emergency brake on a train.
Yeah.
The train engine, which represents the Python interpreter, is humming along.
Mm-hmm.
The wheels are turning, the combustion is perfect. The engine itself thinks everything is completely optimal.
Right, doing its job.
But the conductor, the developer, looks out the window and sees that a bridge is out a mile down the tracks. The engine has no context for the bridge. Only the conductor possesses the broader logical context.
Exactly.
So the conductor actively yanks the emergency brake. It's a violent action, it throws sparks, it halts the system abruptly, but it prevents a total, unrecoverable disaster down the line. You are initiating a controlled failure to prevent an uncontrolled catastrophe.
That is a phenomenal way to visualize it. And, this raises an important question about how large teams build software.
How so?
When you start manually raising exceptions, you realize that errors aren't just accidents. They are an internal API.
Really?
Yeah, they are a deliberate communication mechanism between different modules of a massive system. If the database team writes a function and they use raise to throw a specific error when a query takes too long, they are sending a highly structured message to the user interface team's code.
Oh, I see. Telling it exactly what went wrong.
Right, so the UI can display the right loading screen or an error pop-up. It is a dialogue between systems.
It is a profound shift in perspective.
Uh,
I mean, we really started this deep dive looking at the baseline taxonomy of failure. We looked at how a syntax error means we cannot even speak the language, how a value error means we are putting a shoe in the microwave, and
mm.
how a name error means we were referencing ghosts.
Yeah.
We explored why the interpreter refuses to guess, demanding strictness to avoid silent corruption.
And from that foundation, we explored the architecture of resilience. We built tri-block sandboxes to monitor dangerous execution and accept catcher's mitts to intercept the fallout. And we were careful to never swallow the exceptions that actually demand a system halt.
We finessed the execution flow, using else to isolate the reward of success, like plugging in the TV only after the wiring holds. We utilized pass to communicate deliberate inaction, giving the silent treatment to expected noise.
It's a spam caller.
Exactly.
Yeah.
And finally, we took absolute command of the environment, using raise to yank the emergency brake whenever our own logical rules were violated, entirely independent of the compiler's approval.
What I really hope you, the listener, take away from this exploration is a fundamental shift in your mental model.
Yeah.
When you first start learning a language, a wall of angry red error text feels like an insult. It feels like the machine is telling you that your logic is bad.
It feels personal.
It does. But understanding this architecture proves that professional engineering is never about writing flawless code that never encounters an error. That is a total myth.
Right.
The real world is simply too chaotic, and user behavior is way too unpredictable. Great engineering is about architecting brilliant, resilient ways to manage inevitable failure. It is about building systems that degrade gracefully instead of just shattering under pressure.
So what does this all mean? It means failure is just another data structure. It is just another expected input to be categorized, routed, and managed. And it leaves me with this final thought for you to mull over today.
Let's hear it.
We have just spent all this time analyzing how much energy, foresight, and complex logic developers pour into building these elaborate safety structures. The targeted accept blocks, the deliberate raise commands, all designed to handle human unpredictability and systemic failure inside a digital environment.
Yeah.
But what does that teach us about how we should design our own physical systems outside of the computer?
Oh, that's interesting.
When we engineer our supply chains, our project teams, or even our own daily schedules, do we stubbornly assume that everything will execute flawlessly, like some naive, unprotected script?
Usually, yeah, we do.
Or do we build with the explicit assumption of chaos? Do we have our own accept blocks in our daily lives? Are we designing organizations and routines that can intercept an unexpected impact, absorb the shock, and gracefully keep the production moving without the whole system crashing down?
That is a great question.
It is definitely something to think about the next time your day unexpectedly throws you a value error. Keep asking the hard questions, keep building your safety nets, and we will catch you on the next deep dive.